imaginary numbers are numbers that do not show up on the real number line. So if we imagine the real number line to be the x-axis, the horizontal axis, this is the number line that we're used to. We can point to any number we know about on this number line, whether it's pi, or whether it's 2, or whether it's the square root of 18. We can find that number on the real number line, but imaginary numbers don't exist on there. We can't point to them. And so what we did was we decided to turn our graph, our number line, into a two-dimensional number line. In a sense. So we're going to call the x-axis now the real axis. So that's where we're going to plot our real number part of our complex numbers. The vertical axis then, what we used to call the y-axis, will now be called the imaginary axis. So the way we're going to plot these numbers is very similar to the way we plotted points. The real number is sort of like our x coordinate, and the y value is sort of like our imaginary number is kind of like our y coordinate. So for example, the number 3 minus 2i, I'm going to count 3 spaces on the x-axis and then count down 2 spaces on the imaginary axis. 1, 2, 3, 1, 2, and plot that point right there. So we see that our imaginary numbers don't exist on the number line, they sort of exist above or below the number line. The number -2 plus 4i, the complex number, the real part's -2, so I would count 2 spaces in the negative direction. And then count up 4 spaces, 1, 2, 3, 4, and see that that is where the points, or the number -2 plus 4i is located. 3i is just located straight up on the imaginary axis. There is no real number part to it, so that just counts straight up. The number 4, the real number 4, is located where it's always been, on the number line, 4 spaces, so that's point D. And then finally, -4 minus 3i is going to be located right down there. So our real numbers, our complex numbers exist above and below the real number line. It's important to note how to plot these points because we're going to need that information to find the absolute value of complex numbers. Now remember, absolute value is a number's distance from 0, so it can't be negative, as we said in the past. You can't go out and run -1 miles. Also, distance cannot be imaginary. You can't say we're going to go run imaginary 1 miles. Try to tell your gym teacher that and see what happens. So we have to make sure that we have one real number answer for our distance. So let's go ahead and plot this point, -4 plus 3i, and see if we can come up with a way to find this number's distance from 0. So we just discussed, to plot this, we're going to count -4 on the x-axis, which we now call the real axis for these problems, and then up 3. So that is where the point -4 plus 3i is located. So what I want to do to find its absolute value is to figure out the number's distance from 0. So that's the segment I want to find the length of. Seeing it drawn like this, a lot of people intuitively figure out what they need to do. They realize this is just a Pythagorean theorem question. We're going to turn this into a right triangle. We know the bottom of this triangle is -4 spaces, and we know the vertical side of the triangle is 3 spaces. So we are just going to be doing Pythagorean theorem to find the absolute value of complex numbers. So if I do that, I would have distance, which is my absolute value in this case, is equal to 3 squared plus -4 squared, and make sure that's in parentheses when you square it. It always needs to be. That gets me 9 plus 16, and finally 25. Remember though, we had d squared, so the final step is to take a square root. The square root of 25 gets me an answer of positive 5. So the absolute value of the complex number -4 plus 3i is just positive 5. Now this kind of thinking also gives us a formula, so if we don't want to graph these problems, although you're certainly welcome to graph them, we could do these problems with a formula. That formula, let's go ahead and try that for this complex number down here, -1 minus 2i. So the answer is not, first of all, it's not 1 plus 2i. Some people think just change the signs and make it positive. That's a complex number. You can't have an imaginary number as absolute value as distance, so that is absolutely not how we do it. Instead, it works like this. It was to take our real number and our imaginary number, if we square those. Remember, those are just legs of a triangle. So I'm showing you the formula now for this. Plus the other leg is the other number, so the imaginary number squared. And then we had to take a square root at the end. So that's sort of our formula if you don't want to have to graph all these problems. Just the square root of the real number squared plus the imaginary number squared. So simplifying this to find the absolute value, -1 times itself is positive 1. That's why those parentheses are so important. -2 times itself is 4. 1 plus 4 gets me 5. I end up with the square root of 5 for the distance. Now distance can be irrational, that's fine. But it's not negative, it's not imaginary, and I don't want decimals for these, I just want the square root of 5. Okay? Last up is the absolute value of -4i. Once again, the answer is not positive 4i. That's an imaginary number, and I can't have an imaginary distance. So instead, I could graph this one, which I'll do at the end to show you why this problem worked out the way it did. But let's try that formula again. It was a square root of the real number. This time there is not a real number, so that's just 0 squared, plus the imaginary number, which was -4 squared. this becomes just 0 plus 16, which is the square root of 16, which becomes just a regular 4. So the absolute value of negative 4i is just negative 4. If you think about why that worked out the way it did, think about where this point would be if you graphed it. Negative 4i is just 4 spaces down on our imaginary axis, and if I want to connect that point back to 0, it's just a vertical line. I can count that and see it was just 4 spaces.